One.
All right. Hi guys. Today it's another Friday, so it's another session with us for Arc Originals 78. This Friday it's a little bit different from any other Fridays in the past few months because this Friday I think it's the start of our phase 2. We would be able to kind of like go out and dine. Um, yeah, and I think in the following weeks, like some of us would be seeing each other. But please do remember to wash your hands and keep your mask on. And without any further ado, let's get into RK. So again, shout out to Shopee and engineers for providing us with the resources to make this happen. And COCs, as usual, please do not record our live streaming. Please do not post advertisement in your live chat and say nice things to each other. So Singapore CSS is still looking for speakers. Do reach out to them or reach out to Gawe if you have something to present. We are at it. If you have something to speak at RK, if you want to share with us maybe some cool insights or some new discoveries, do speak with myself, Gawe, or visit this link if you are a bit shy. So today's topic is something about the obscurities of the Bézier curve explained to my computer engineering. There is some obscure things appearing on the screen as well. I have no idea what's happening. It's a little dim, and there is a extra character over there. I'm not very sure of it. What's happening there? It will be presented by our speaker who has been talking with us about really random things from rock climbing to pixel art to typography, React, and today she'll be talking about math. So without any further ado, please welcome Gawe. Gawe, please.
Hello, can everybody see and hear me? Can you see and hear me?
Yep.
Let me share my screen. Because I need to draw today. This math class. Right. Okay. Okay, let me wait for my screen to show up. Okay. Looks like my screen is showing up and everything looking good. Okay. Okay, so let me get started. So I am sharing about Bézier curves today. Thanks for the intro. I also don't know what the obscure effect that was happening on your screen earlier on, but first of all, let's correct our pronunciation. Bézier, okay, French, pronounced with an A ending sound. So let me switch over to my slide. I guess the original question that I was asking was, well, what is this CSS function that appears in my screen, in my code? So in our code base, there's a full file of magic numbers, and out of all those magic numbers, everything else is making sense. Like, it's more often a color or a pixel value, except for these lines. I think initially I was not even sure whether I was spelling them correctly. But this whole line is just saying, like, don't touch me, right? So what this is doing in CSS was that it defined some kind of curve for the animation that is supposedly not the default one, and sometimes the designer would like some customized easing function, and that's when we use the Bézier curve. But then because it is using some numbers, like 4 numbers between 0 and 1, or maybe sometimes negative, it's not making sense. Like, I don't like magic numbers, so I wanted to know like what these numbers mean. So if you do a little bit of research, you might you might end up here. This is Google's material design, and it has a bunch of easing functions, and some of them would look like this. So it looks like something dropping, right? And then and this one looks like something showing up. It looks like someone tossing something up, and it's slowing down. And there is some like more complex curves. So I guess then the question is why these numbers can represent curves. And if we keep doing the research, we actually quickly move away from CSS, and we will land on like researches about like computer graphics and how to model curves and all that. And as it turns out, initially this problem was not a computer engineering problem at all. It was solved much earlier than computer engineering encountered, or say computer graphics encountered this problem at all. So back in the 1950s, the automobile industry was like they were producing cars like this, and one of the engineers, Pierre Bézier, he was working at Renault at the time, and he was looking for a way to modulate curves, basically to represent curves in his design. So he proposed for the company to invest money in this research, but got declined. And he resolved to researching it anyway. But then the management team also was unimpressed in the beginning. So like many other inventions, the initial acceptance wasn't great. So this is Pierre Bézier. So how did he eventually figure out a method that worked and that we are using like nowadays in nearly all aspects relevant to graphics and modulating curves? So if we look more closely, the initial problem is we're trying to model curves. But then before we know how to do it, like the whole problem is not easy. Okay, wait, I think I did not switch back to my slide. Okay, so I think this is not responding. Okay, sorry for skipping a few slides. This was the Renault car. That was the first car designed using the Unisurf CAD, which was the method that Bézier developed. So the initial problem was to model curves, and without like existing method, it actually wasn't ready. And here are some of the attempts. It may look a bit weird to you. That's because, well, we haven't figured out a good enough method yet. So anyway, here is one attempt. How this works is you have a circular curve and you attach that to some kind of like frame, and then you kind of like squeeze the frame to to change that to another shape, hopefully to model an eclipse. And here's another one. So what you do here is you use a torchlight, and you let your torchlight go through some kind of shape. And when the light lands on the wall, you will see the shape kind of formed into another shape. And then you take a paper and kind of record down the exact position of where the curve goes. There is even one involving like springs and taking a string and all that. So it wasn't easy. So how can we go about like solve this problem? So we might look into some theoretical foundation, and mathematicians say that as long as we're in a closed interval, there will be a polynomial approximation for all like smooth functions. And then, but engineers are definitely not going to be satisfied with the fact that there exists. It needs to be constructive. And so maybe to attempt to solve this problem, maybe get back to some of the intuition. And it feels like we're trying to, if we are to try to modulate the curve that is showing up there on the wood cutting, maybe we can get some inspiration from there. So it looks like what we're doing is we're cutting one edge and going through and trying to go to the other edge, right? So this looks like what it is happening. And here is the Wikipedia GIF that you can see from here. So we're kind of doing something like this, like we're moving from an original point and we're moving towards the end point. And in between, something is happening. Maybe it's a bit too fast. So let me try to break that down for you. Okay. Right. Let me remember to come back. Okay. So what is happening here? Let me just try to draw what it looks like. So here is my first point, and it looks like it's going upwards this way. Here's my second point. And then so it looks like we're doing this. And so how do we find out? So on Wikipedia, there is a point that's the black point is a point on the curve. So how do we find out that point? So what you do is, so we're trying to depict a progression that goes from 0 to 1. And normally what we do this is we give it a parameter called t. So what t represents is a progression. And so let's say the progression is somewhere here. This looks like somewhere around like 70% or 67%, somewhere around there. But then we don't have to know the specific number now. We just know that this is the progression that we're looking at. And we want to try to find the progression on the first line. So somehow that lands here. And then on the second line, as you can see, the second line is of a different length of the first line, but we want to find the same progression. So somewhere around like 2/3, somewhere here, okay? Would you agree with me? Actually, let me change the color. Okay. So the first point is around here. Okay. Second point around here. Okay, maybe. Right. And then what you do is you connect these two lines. and you get one line segment instead of two. And then finally, what you do is on that line segment, you're still trying to find the same progression. Okay, so that looks like somewhere here to me. Okay, so that point will be the point on the curve. And this is by plugging in P equals to this progression. But then you can plug in a bunch of T's, and you get many, many points. And then eventually you will get some kind of curve that looks like this. Okay. It's not a great drawing, but this is the idea. So so it turns out that what we did was an algorithm called the Cathedrals Algorithm. So the Castillo is also French. Back then he was working for another car company, Citroën. And in fact, the Castillo was the first one to find out about this algorithm. And Bézier was actually the one who later on formalized it and popularized it. So, so what exactly does the Cathedrals algorithm do? Let me give you another example to get more familiar with the process before we look into the pseudocode. So, so this time, let's use let's use this curve. So this is our first point, and maybe this is the second point. Okay, and then let this be a third point, and going down here. Okay, and this time let's give them coordinates, and for ease of computation, let's just assume that this point is 0, 0, and this point is 0, 4. This point will be 4 and 4. And then this one is 4, 0. Okay. So these will be the original points. And how do we find out the final point? So similarly here, what we're doing is we first will try to find another line segment. So let's okay, so so let's try to find out the midpoint. So point will be T will be 0.5, and then what will be the first? Let's call it generation. Okay, what will be the first generation? So it looks like the first point will be somewhere here. Oh, I don't think I have good enough approximation, but yeah. Anyway, so the first point will be here, and the coordinates will be 0 and 2. And looks like my second point will be here. Is it the middle point? Oh, good enough, I guess. So the coordinate will be 2 and then 4, right? Do you agree with me? Please correct my math if I'm doing it wrong. And then the third point will be here. And then the coordinates will be 4 and 2, right? And then what you do is you connect these points. Well, I'm really grateful that it actually picks it up. Okay. So next, so as you see here, I am losing one line segment because I am connecting the 3 points on the line segments in the 3 lines from the previous generation. Okay, so how to find out the next generation of points? You find the middle point again. Looks like somewhere here. And then the coordinates will be the average between 0 and 2. That will be 1. The average of 2 and 4 will be 3. Okay. And then this one looks like, I know it's not very good, but please bear with me. This one will be 3 and 3. And then you connect these 2 points. Okay. Well. And then finally, this point. We're left with only 1 point now, and that point will be final point on the curve. And the coordinates looks like it will be 2 and 3. Okay. Yeah. So once again, if we do this for many t's, we will get many points, and then our final curve will look somewhere like this. Right. So if we are to summarize a little bit of what we did here, we start with those grayish points, and let me call it P1, P2, actually P0, P1, P2, and P3. So I'm having those points, P2, P3, and then P4. And then we have referred to them as the zeros generation. So P1 of 0 generation, P2 of 0 generation, P3 and P4 and so forth, right? So these are our 0 generation points. And how did we get the yellow points? What we did was we take P0 and P1 of the zeros generation, and we use these 2 points to figure out the first point. So let's call it P1, and this will be the first generation of the first generation. And how do we get these? I'm not going to do the math here, but you will have to believe me that this is P1 of 0 multiplied by 1 minus t. Intuitively, what this means is when t is really small, like when this is 0, this is happening nearly exactly what the P1 is doing, okay? So because it's multiplied by 1, and then we're multiplying P2 by t. So what this is saying is when t is really small, like when it's 0, it is doing nearly nothing of what the P2 is doing. But when you move along, it is doing more of what the P2 is doing. So so this is how we get P1 of 1. And likewise, how we get P2 of the first generation. Actually, let's be more consistent. This is not P1, this is P0. P0. And then P1 of 1. So P1 of 1 is, we do the similar thing, but we're taking, oh well, sorry, I fail with indices. So 0, 1, 2, and 3, okay. Yeah, so similarly, what is happening here is you multiply the previous generation, but 1 minus t with the first point and times t with the second point. And then similarly with this point. So this will be P2 of the first generation. Okay. And then how do we get the third generation of point? We're doing something very similar here. And then for the for the final point, we're multiplying by 1 minus p and t. And we get our final point on the curve. So, so if you still remember some college math, the final, so we start from all the 0 generation points, and these are the points that we know the coordinates of. we know these are 0, 0, 0, 4, 4, 4, and 4, 0. And all of these intermediate steps, we are multiplying them either by 1 minus t or t. And these are something called a Bernstein polynomial. You don't have to know this, but basically, if you factor these out, you'll get a bunch of coefficients. And those coefficients will formulate a nice triangle that looks somewhere like here. So it will be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This will be the Pascal triangle. I think and then eventually the final point, it will be a bunch of like t terms, and 1 minus t terms, and then summed up together. So this is the process. Is it a bit messy? Well, but I kind of find the triangular scheme kind of cool. So it turns out that this is actually referred to as the triangular scheme. So what is happening is in each generation, you're getting one fewer point, but you can deduce all the points from the previous generation, and then eventually you land at the final point that is supposed to be on the curve. Okay. So this is the Cathedrals algorithm and the triangular scheme, I think. All right. And so I hope that helps us understand the pseudocode a bit easier. So I think this version, the function naming is can be a bit confusing, but so draw a curve takes a bunch of points. These are your control points, and it's also a function of t. So when we draw the final Bézier curve, what happens is if we are left with only 1 point, that means we are we have found our final point on the curve, and so we draw that point. So on the screen, drawing a bunch of points drawing a curve means to drawing a bunch of points on the screen, and then you connect all those points with a line. But here, if we're left with only 1 point, we will draw the final point. Otherwise, that means we haven't finished yet. We're still in the generation thing. We're trying. So what we're doing is we're trying to deduce the next generation of points from the previous generation. And how do we do that? So we create the array, and the size is going to be previous generation minus 1, because we're getting 1 fewer point in each generation. And then we populate the points in that generation. So for all of these points, what you do is you multiply the point with 1 minus t of the first point of the previous line segment, plus t multiply the second point, okay? And then finally, this is a recursive procedure. You will call the draw curve function again with the new points, which has 1 fewer point, and the same t. So eventually you will reach 1 point, and then eventually you will find out what that point is on the curve. Right? Okay, so the pseudocode doesn't look so hard to implement. So I do have an implementation in React, and it turns out that there's a very natural implementation with React. So I'll show you how I did it. And so in my app, the first section, this is a simple controller for the user to add or remove control points. So what I get out of here is a few like utility functions or callback functions, but then what is really important are the control points. So after I get this control point, by the way, can everybody see the code? Well, I'm not hearing complaints, so I'll just assume that everybody can see the code. So after I get a control point, what I'll do is I'll call this hook called use draw curve. And I will show you what this is doing later on. But for now, please understand that what this return is the ft function. What is the ft function? So the ft functions are the function you can later use to populate however many points you want on the curve. So in my case, I'm setting the step size to be 500. That means I will plug in 500 t's from 1 over 500 up until like 499 over 500. So these will be the points on the curve. And finally, I'm using SVG because SVG can help you draw either paths or circles really easily. So I'm drawing some other stuff, but let's focus on the curve. So finally, I'm taking all of these points, and for each of those points, there will be 500 of those. I'm drawing point on curve. Okay. We'll look into this. Actually, we'll look into this component later on. So let me show you the cathedral algorithms implementation. So this is a draw curve hook. So the draw curve hook will take the control points, and then it will return a callback that calls draw curve with these control points. Please ignore these arrays for now. And so the draw curve is following exactly what I just showed you. So once again, please ignore the left and right for now. Of course, if there's no points, we're not doing anything. And then if there's only one point, that means we're reaching the final point on the curve. And so ignoring the left and right thing, we're returning the point, okay? And then otherwise, we're creating the new array. Let's ignore the left and right thing again. And in the loop, what we're doing is we're populating the next generation of points. And so this is the exact calculation from the pseudocode. And then I have my new points populated. And then I'm returning the recursive step that calls the new draw curve with new points and t. Okay. Do you think this will work? So here is the f, and then this will be the curve. Do you want to try some higher order, like some crazy like Bézier curves here? Yeah. So all of these will be the control points, and then your this app is drawing a bunch of points on the curve. So if we're moving like really fast, you can actually see the points here, right? Okay. So right, okay. Get back to the slide. Oops, sorry about the loading. Okay, this doesn't seem it's getting anywhere. So I think I don't need to, since I don't need to draw anymore. Let me switch over to using my laptop to share. Okay. So okay, is my screen showing up? Yeah, I think so. Okay. So next, I want to share with you some of the properties of Bézier curves. Okay, first is the fact that the whole curve will stay within the polygon that defines the curve. So this means what this implies is you are guaranteed to have a bounding box for any Bézier curve. You do need some computation, like like the bounding curve for this curve will not be the exact control polygon, but you can still figure this out with some simple calculation. So yes, you are guaranteed with a bounding curve, a bounding box for the curve. And then second, you can break a Bézier curve into smaller pieces. And guess what? Each of those smaller pieces will still be a Bézier curve. So what is the geometric picture that you will be seeing? What happens is you can find a T, and if you fix that T, you can see that does the first half as well as the second half still look like a Bézier curve to you? I think the intuition is not that hard to get over, because if we consider the whole process as formulating something from the starting point to the end point, right? From 0 to 1, right? At each single point, I can regard the first segment as a 0 to 1. I'm ending here, and this will also be the starting point of the next segment, right? So, so this is what the left and right thing that you were seeing previously. So after that load, I'll show you again. Okay. So where are the files? Okay. So okay, actually before I tell you about the implementation, I need to tell you one more thing. So not just the fact that both of these two sides are still Bézier curves, but also all the control points of these curves are already calculated. So what are the control points? So let me open my app. So the control points for the first segment is the T point, the current point. And then this one is the control point that we use to calculate this T point. So this was the progression T. So this was the control point that we used. And same here. This is the control point on the second line segment. So all of these control points are already computed. All you have to do is, so you can see that these are the control points here. So all you have to do is do some logging. So here is the left and right array. If we're at the final point, we're adding the final point into both the left and the right array. Otherwise, we're doing some logging here. We're adding the control point of the second to last generation to the left array, and then the next point to the right array. So I think we might need to formulate our thoughts at a private time, but basically here is what it's looking at. So this control point is the control point from the second to last generation, and this one is the third to last generation, and this one is the original point. So we're doing some logging and returning the left and right arrays, and here is how you get the broken down curves. And here we're actually breaking it down only once, but you can actually recursively break them down, and you won't have to compute any more control points at all. All of the control points are already computed. Yeah. So, I actually had the diagram showing where the control points are. Anyway, so this is the pseudocode that I already showed you the code. So 1 and 2 together 1 was the bounding box, and 2 means you can break the curve down and still get Bézier curves. What 1 and 2 together implies is that you can find the intersections of any two Bézier curves. What you do is you can continuously break them down into smaller Bézier curves. Once you get smaller Bézier curves, your bounding boxes will get more refined also. You will get one set of smaller bounding boxes on curve A, and you'll get another set of smaller bounding boxes on curve B. And then either you will find no intersections at all, which means your two curves don't intersect, or you will keep finding intersections until you reach pixel level, and you still find intersections. What that means is the curve, either the curve do intersect, or they're really, really close to each other that your pixel level cannot catch the gap, and you will treat that as the two curves are intersecting. I think this slide is not in the right order. I already show you the split curve implementation. So next slide. So next, you can join two Bézier curves to form poly Bézier curves. Normally, when you join those, you will add some smoothing conditions. So what do I mean by that? So here is a diagram showing what's happening. So this point will be the joint, and note how the point moves through this point as if there is no change at all. There is no change, but if you move this, you can see two things change. One is the point turn, right? Because this vector is turning, and also the velocity, the magnitude of the velocity change is moving much slower than previously. But then if you want to join two Bézier curves into a poly Bézier curve, what you want to do is you want to match both the magnitude and the direction of these two vectors. So if you get that intuition, I think it should not be it should be a next step for you to understand why when you join these curves, these two line segments should match, right? This is why if we're using like Figma or Sketch or anything, and let me create a new file. And if I draw a curve, and if I try to like tweak this curve, right? Okay. You will see these two vectors coming up, and they're always of the same magnitude, pointing away from each other. This is how you get the smooth condition of joining two connecting Bézier curves. Right? And then it should be apparent to you that if like this and this has to equal, and then this and this has to equal, and this and this has to equal, and this and this has to equal, that means if you move one curve, okay, this is the wrong thing to play around. If you move one curve, your whole curve is changing, right? So this is very bad. So this is a poly curve formed by quadratic, which means 2-degree Bézier curves. So what you want to use is 3-degree Bézier curves. So these ones, it won't affect the whole curve. There is a Bézier game that you're supposed to formulate some curve by dragging things around. It's kind of hard. I cannot play this game. Maybe you can give it a try. So I think we're already seeing some of the limitations. First one is non-localness. Basically, what this means is when you're changing one part of the curve, the whole curve is changing. And then second one is you cannot precisely model shapes like an eclipse. So that's some of the limitations that Bézier curves have. I'm running out of time, so let me just quickly share a bit about Bézier curves in browsers. CSS easing functions, of course. So you might have run into this website. This is qubit Bézier curve, and now you can understand these actually 4 points, but these are actually 2 points of degree 3 Bézier curve. Why? Because the first point and the final point are already fixed, and you only need to specify the second and the third point. So this one is the second point, this one is the third point. And what this means, means is the x-axis is time and y-axis is progression. And what this is doing is, in the beginning, it's moving really, really fast. It's like right after moving away from 0, it's jumping right over to nearly the midpoint. This is what's happening, right? The ambient dot is actually making sense. And another thing I think is really cool is that actually you don't need to understand what is going on with those points at all. All you have to do is you just drag around and you can get a sense of what is happening. And so our designers can actually play around and get a number and give us the magic number, and we are able to program what the designer wants. So this is something really, really cool I find about Bézier curve, because you have the geometric picture on one side, and then on the algebraic side you have really performing computation, and all you need to save are 4 coordinates. So it enables you to compute, or not compute, to implement implementations like these. You can use different Bézier curves to have this effect. And then SVG paths. So if you look into SVG, some of the commands you have moved to. Okay, so when you draw a path, you have a few commands that you can use. M means to move, and L means line, draw a straight line. But then there is a curve command. What this does is it draws a qubit Bézier curve. And you also have qubit Bézier curve means it's degree 3. This one means it has 2 more control points other than the original point. And then you also have, I think I was saying something wrong. I'll fix that later if I did. And then there you have the quadratic Bézier curve, which will draw the quadratic curve that goes to the next point that you plug in. Similarly, Canvas also has curve tool, also implemented with the poly Bézier curve thing. And then there is font glyphs. This actually goes beyond browsers. So I think previously Tiger shared with us how font glyphs are saved in a computer. These are actually saved with a bunch of Bézier. Okay, so it's a more generalized form of the Bézier curve called the B-spline curve, because it's to go around the localness. So all of these are a lot of Bézier curves connecting one another. There's even a whole programming language powered by Bézier curve. So PostScript is used by Adobe as well as a lot of printers. So it defines objects with vectors and then it will raster them on the fly. Why can you do that? Because you can compute the curves very, very fast. Yeah. So sorry, I'm going a bit too fast in the end because I was going too slow in the beginning. But I hope you get a feeling of what is going on with Bézier curves. There are a lot of references. All of these are about fonts that you can read. It's really, really cool. So that is the cool things I want to share with you. And we still have some time for questions. don't know. I actually don't know what's going on with the chat. Because normally I would be like chatting with people. Yeah. I guess I'll stop sharing for now. Ken, are you with me?
Hi.
Hi.
So,
Yeah.
I think we probably have to fix our streaming because it's a little bit laggy. But I think
okay.
for those animations that you have shared, we'll share them later on in the issue, so you can have a look, and you guys can have a look and look at the animations that we weren't able to show.
What animations? Oh, never mind. Okay.
Yeah.
Sure.
Yeah, I think in general, like there is no questions. Yeah,
Okay.
but people were just like, oh wow, like you have created the playbox, I don't know, the sandbox for the Bézier curve, and then I totally didn't know that you can actually have the lines crossover. Right, the Bézier curves having a line crossover, because usually just
Wow.
be
Oh yeah.
not crossing over.
Well,
Yeah.
okay.
Yeah.
Well, I hope you like it, and yeah.
Yep,
So
we
I
definitely
think yeah. So I think that is all I have to share. Feel free to grab me if you want to talk about curves or want to know what next. Like what next? So there are actually more curves that I ran into. And then after curves, you can have surfaces. So those are also really, really cool. So yeah, I guess.
Yeah. So thank you again for your sharing. Yeah, maybe next time you can share with us on how surfaces work with curves. Yeah, and thank you all for tuning in for RK today. And hopefully we'll see you guys next week. Some of you guys in person, some of you guys online. So, yep, thank you. Bye.
Okay. Okay. Please stop this. Okay. Why? Oh.